Okay, so what I'm going to do is I'm going to start working through, there are a couple of problems that I want to talk about from chapter 3.5, which are about rotations around axes. So this is chapter 3.5, and the first thing that we're going to do is question 10. Okay, so question 10 is we want to determine the volume of the region obtained from this function and rotating around the x-axis. We were told specifically to go around the x-axis. Okay, and the function that we're looking at is y equals sine of x, and we're looking at a region from 0 to pi. Okay, so I always like to draw these things out so I can visualize what's happening. Remember, our sine function is going to go up and it's going to come down, and it would normally kind of go like this, right? So this is the region here, and let's make a note. We're going around the x-axis. Okay, so it's going to look like this egg-shaped function here. So we're going to get this, and it's all solid. Okay, so we've got this sort of solid shaped function that we're working on here. Okay, so now because we're going around the x-axis, right, I'm going to use the disk method. Okay, so the disk method says I've got a circle here, and the circle has a radius that goes from my x-axis to my function itself. This is my radius. This is my radius, this is my radius, this is my radius, this is my radius, okay? So the volume in our disk method is going from our x1 to x2, 0 to pi, and we're going to go pi r squared. This is the area, the cross-sectional area of that little sliver of a circle, and we're going to go times dx. dx tells us the thickness, that tiny little thickness of that little circle that we're doing. This here, that r squared that we're doing, right, we said was the distance between our x-axis, which is y equals 0, and our function, which is y equals the sine of x. So our volume, 0 to pi, I'm going to go pi r squared, so this is sine of x squared, that's our radius, dx. Okay, so I want to be able to integrate pi sine of x squared dx from 0 to pi. I just want to remember I've got an identity for sine squared, which is equal to 1 minus the cosine of 2x all over 2. That's one of our trig identities, which I'll write it out as 1/2 minus 1/2 cosine of 2x. All I did was distribute that 2 into both of those terms. Because that's the identity I'm going to substitute into here so I can then integrate more easily. 0 to pi. Actually, what I'll do is I'll bring the pi out. Pi, right? The pi is just a constant. So I'm going to bring that outside. I'm going to substitute the sine squared with 1/2 minus 1/2 the cosine of 2x dx. Okay, which means I'm just going to distribute these and I'm going to integrate them essentially like the power rule. So I'm going to get pi times 1/2 dx minus pi times 1/2 cosine of 2x dx. Okay, and both of these are going from 0 to pi, 0 to pi. Okay, so when we go to integrate this, right, that's pretty straightforward. I'm going to get pi over 2, right, that's the 1/2 times x, and I'm going to go minus. So I've got the pi over 2 because it's from the 1/2 before. I've got this 2x here that I need to take into account. So that makes it pi over 1/2 times 1/2, so pi over 4 sine of 2x, and I'm going to evaluate those from 0 to pi, which is going to give me pi over 2 times pi minus pi over 4 sine of 2 times pi minus, put a little bracket around it, minus pi over 2 times 0 minus pi over 4 times the sine of 2 times 0. Okay, this is the 0. Sine of 0 is 0, so I'm not going to worry about that. So sine of 2 pi is also 0. Right, so I'm just basically looking at pi times pi over 2, which is just pi squared over 2. Okay, and then that's my answer for question 10. We're going around the x-axis, so I'm going to use the disk method for it. All right. The next question I actually want to talk about is question 39. Chapter 3.5, question 39. This one wants us to do both the shell method and the disk washer method. So they're trying to tell us, make us see that one way is going to be easier. So we're looking at, we've got the graph y equals sine of x, because we're looking at that again on the same interval 0 to pi. Okay, and we're going to go about the y-axis this time. Okay, so let's draw this out. So before we went about the x-axis, which is why we did the disk method, now we're going to go about the y-axis. So we would expect our volume to be different because we're going about a different axis here. So let me draw this out. So this is pi, and this is 1. So from 0 to pi, my sine function, this is my y equals sine of x. 0 to pi, this is like the shaded region. This is the area that we're going to be doing. Now remember, I'm going about the y-axis. I always draw a little arrow to remind me what I'm doing. So if I'm going about the y-axis, I always initially think shell method. It's going to be more straightforward. But what I'm going to do is I'm going to draw this out. So it's going to rotate around to here. You can imagine this thing here scraping out a circle. And it's going to scrape out a circle in the back here too. So we've got these things here that are making this shape. So it's got this kind of a mound, like as it's going around here. Okay, so it's flat on the bottom, okay, but it's kind of got this like a piece, and it's going around like that, kind of like a donut if you were to cut it in half. Okay, but if the donut didn't have any hole in the middle here. Okay, all right. So we'll do our shell method first. They want us to do the shell method first. So part A says shell method. Now the shell method for volume is 2 times pi, right? And we're going to go 2 times pi. We're going to go from 0 to pi. That's what we were told to do. Okay, 2 times pi times the radius. So wherever we are in the x direction tells us we've got this circle that's happening, right? So it's forming a circle as it's going around. This whole piece is my diameter of the circle. This piece from here to here is the radius of my circle. So wherever I'm at in the x direction is my radius. Okay, for this particular problem, we don't have to do any other kind of funny manipulation with the x. We'll go through some other problems at a later date where we work through what these things can look like if the problem is more complex. The height, right? We want to be able to calculate the height of this. This is going to be our function, sine of x. There's no pi r squared, okay? 2 pi r gives us the circumference. We're talking about a circumference. So 2 pi r gives us the circumference of our circle. This y, right, sine of x, gives us the height of that circle. Dx gives us the thickness, that tiny little sliver of thickness for our circle. Okay, so what I'm looking at is to calculate the volume, I've got 2 pi, 0 to pi, x, sine of x, dx. Okay, so when I go to integrate that, I need to think about integration by parts. You will be asked to show what the antiderivative is on some of these here, so make sure that you know how to do this. Integration by parts, remember, is uv minus the integral of v du. So I have to be able to assign different pieces. So my u, the most simplest piece is x. The du is going to be the derivative, which is just dx. My dv is going to be sine of x dx. I integrate that to get v, right, which is going to give me minus the cosine of x. Okay, so I'm going to plug these different pieces into my uv minus v du format. Okay, so all of this is multiplied by 2 pi times pi. So I'm going to just put a bracket there. So u times v, so this is x times the minus cosine of x. Put parentheses so you don't forget and think it's subtraction, because it's not. Minus integral from 0 to pi. I've got minus the cosine of x, right? So this is v du. Okay. All right, so let's go ahead and multiply these out. So this is 2 times pi minus x cosine of x. Right? This minus comes from the coefficient of cosine. Minus a minus becomes plus, okay? Because when I integrate cosine, I get sine. And I'm going to evaluate this whole thing from 0 to pi. Okay? So I'll just start plugging things in. So I get 2 pi minus pi cosine of pi plus the sine of pi. The parentheses minus 0 plus the sine of 0. Okay, so 0 sine of 0 is also 0, so I'm not going to worry about this whole bit here. Okay, so let's start thinking about this one. Cosine of pi is minus 1, so minus times minus makes this a positive pi. Sine of pi is equal to 0, so I'm looking at pi times 2 pi, so my total volume is equal to 2 pi squared. Okay, remember, this is different than the problem that we just worked on, because we, in this one, are going around the y-axis, so we do expect our volume to be different from when we went around the x-axis. Okay, so that's the shell method on this particular function. Now the disk method, if I'm going around the y-axis, the disk method can be more cumbersome. if you're going around the y-axis, really you want to think about your shell method. That's really the way to go if you're going about the y-axis. Okay, so let's write down what we're given. Y equals sine of x. We're going from 0 to pi. Okay. Now, with the disk method, and I'm going still around the y-axis. Okay, so I need to be thinking about how I'm going to make this happen. So this is going to be, this method says pi r squared. Okay, which means, and this is dx. So pi r squared means, but I'm going about the y-axis, sorry. So this is going to be times dy. Okay, so I have to get this function here as x equals something. Okay, so I need to take the inverse. I have to take the inverse of both sides, so I get x equals. This is going to become x equals inverse sine of y. Now remember, in my sine function, if I go along the x, I'm going from 0 to pi. But because I'm doing a dy, right, this is like a little sliver here and a little sliver here that I'm actually doing a pi r squared about. My y is going from 0 to 1. Okay, so when we do the disk method going around the y-axis, not only do I have to change the function y equals to be x equals, I have to change my range because this is x goes from 0 to pi, but now I need to go y equals. Okay, so let's start putting things together. So I've got my volume is going to equal pi r squared, and we're going to go from 0 to 1. This is dy now because we're going still about the y-axis. So let's put it together. So this is going to equal, I'll bring the pi out, 0, 1. Now r squared, r is my radius here. This is my inverse sine of y squared dy. Already I'm unhappy. I've got inverse sine squared. Okay, so what I'm going to think about again is maybe integration by parts, right? I've got a sine, inverse sine times an inverse sine. So that's kind of how I'm going to be thinking about it. So, or inverse sine squared, and then a dy is one of my dv's. All right, so let's write it down. So my u is equal to inverse sine squared, inverse sine of y squared. Then my du is going to equal to 2 inverse sine of y all over 1 minus y squared, and this is dy. Kind of a mess already, right? My dv, I'm going to make simply my dy. When I integrate both, I'm going to get v equals y. Okay, so remember, integration by parts is uv minus integral of v du. Okay, so we're going to start putting it together. All right, so u, so I'm going to plug in u, so inverse sine of y squared times v minus the integral of v y times du, 2 inverse sine of y, 1 minus y squared dy. Okay, and then this is all being multiplied by pi. Oops, I need to squeeze that pi in there. Okay, and this is going to go from 0 to 1. We're going to evaluate it from 0 to 1. Okay, it kind of comes out like a mess, and I'm going to stop here because I'm just setting up the integral, but you can already see that when I'm going about the y-axis using the disk method, it's often not very elegant, which is this is a good problem to exemplify why. If I'm going about the y-axis, I want to be able to use the shell method because look relatively how much more simple things were and how I was able to work things through versus the disk method where I needed to convert the function as x equals some function of y. I needed to redefine my bounds of integration. I had to square it. I mean, it just kind of blows up in complexity. So I'll stop here. Okay, and then just say we need to use the shell method.